way it's going to work is our speaker, Dr. Robin Metcalfe, is going to give a talk on, it's a Jupiter mission, the Clipper, an update on space. Well, you can read it up there. You can read. That's what it's about. Robin is, in addition to being on our council, thank you very much, Robin. Robin is a professor of natural science at York University. She's been teaching astronomy for 25 years. She started when she was 7. Robin's PhD research pertained to extragalactic astronomy, but her current interests are in the search for life beyond Earth and the implications on a discovery like that on humanity. I will leave Robin, since we're short on time. You were all free to read the little bio up on our website. So I would ask you to welcome Robin.
Okay, here we go. Thank you for the introduction, Alan. Wait, Alan. The clicker is not controlling the PowerPoint. It's controlling your. Yes, please.
Oh, okay. So mouse over here, click. Now go.
Nice. Okay. Okay, funny story. I'm of the generation that came of age in the 80s. And so anytime there's any kind of 80s night, you can be sure to find me there. I will dance very poorly to 80s music for as long as my child of the 80s feet can hold me up. So why on earth am I telling you this? Well, on Saturday, November 23rd, I attended a retro night at the Phoenix Concert Theater. It was part of a series of a long goodbye to this venue that's been around ever since I was a teenager. And as you might expect, at an event like that, one tends to stay out quite late and imbibe more than one normally would. And so, full disclosure, on Sunday, November 24th, I spent most of the day in bed recovering, which is why it was so interesting when I finally got out of bed in the late afternoon. I checked my phone and I found the following text message from Swapna sent at noon that day. Hi, Robin. I hope your weekend is going well. I was hoping you could present at our speakers portion before our AGM in February. Please let me know. And then apparently I responded 20 minutes later, okay, I could give you a summary of upcoming space missions. So apparently I was penciled in. I have zero memory of having that conversation. And so I now had two options. I either confessed to Swapna that I agreed to this while not entirely conscious, and I now have to renege because I have no time to put a talk together, or I just suck it up and accept the consequences of my actions and somehow whip up a talk worthy of this awesome audience. So obviously I chose the latter, but owing to a really serious shortage of free time that I have these days, I decided to multitask. And I created a lecture that I had to do anyway for my a course I teach in the summer. It's called The Science of Spaceflight and Space Exploration. And it is a course designed for non-science majors. So I start out with about 150 students. They typically have taken no math or science in the last, or since grade 10, really. But they chose the course because they are fascinated by spacey stuff. They just lacked confidence in their ability to do the math. But by the end of the 2-month term, the summer term, they are able to do some really cool stuff that they're quite proud of. They know how to compare gravity fields on different worlds, and they understand why certain space maneuvers require more rocket fuel than others, and why that makes part of the solar system a lot harder to explore. And most importantly, they end up with a big picture understanding of the ways in which space-based exploration is a benefit to humanity. So the course is divided into the lessons that you see on the slide, and each term I choose a currently ongoing space mission and I weave it into each lesson so that the content can be applied to real world contexts. And what I hope happens is that after the course, the students get inspired to continue following the mission after the course is over. So this upcoming summer term, I'm going to focus on 2 recently launched missions to the Jovian system they're a really good choice because they're not going to get there until the 2030s. So that means they can reuse this material for the next 5 years. But also, these missions are probably the most likely to lead us to answers about whether or not there is life in our solar system beyond Earth. And that discovery, even if it's just like microbial life or life that can't communicate with us and can't send us microbial cat videos, that discovery, it has enormous impact for humanity in unknown ways, but I would like to think in a unifying way, in a way that reminds us of our shared humanity. So what I have prepared for you and also for my future students is an overview of the current missions to the Jovian system. And thank you all, and especially to Swapna for this opportunity to get my summer course material developed so far in advance. And of course, the moral of the story is that sometimes something good can come from a really bad hangover. Okay, so back in 2002, I was at the annual general meeting of the Canadian Astronomical Society, CASCA, and the evening public lecture was a talk that I was absolutely privileged to attend. I never forgot it. It was given by Dr. Jill Tarter. Back then, she was the director of the Institute for SETI Research, SETI being the Search for Extraterrestrial Intelligence. And the talk was called, Why Should We Search? So there was a few hundred people in attendance, mostly academics. And it felt to me, as we were waiting for the talk to start, that there was a lack of seriousness to the audience, because back then, anything to do with SETI wasn't really considered serious research. But once the talk began, Dr. Tarter very quickly had our rapt, undivided attention. She's a very, very compelling speaker, and her ability to sway that very skeptical crowd was palpable. I suspect that everyone in the room walked out of there convinced of the value of searching for extraterrestrial life, not because there's currently any evidence to support that it exists, but because there's immense value just to the search itself. As Dr. Tarter explained in a TED Talk that she gave in 2009, over the millennia, we've seen where tribalism leads. We've seen what happens when we divide an already small planet into smaller islands. And ultimately, we actually all belong to only one tribe, to Earthlings. And SETI is a mirror that can show ourselves from an extraordinary perspective and can help to trivialize the differences among us. If SETI does nothing but change the perspective of humans on this planet, then it will be one of the most profound endeavors of history. So in other words, whether we find extraterrestrial life or not, the search itself is likely to help us humans evolve in a more unified way, because it will force us to consider that from the perspective of aliens, we humans were far more alike than we are unlike. Now, SETI researchers focus primarily on the search for intelligent extraterrestrial life, so they look for technosignatures in other solar systems. But in another talk, Dr. Tarter also discusses the importance of the search for life in our own solar system. So she said, in the next couple of decades, as we explore Mars and Europa and Titan, the discovery of any kind of life there will mean that life is abundant in the Milky Way. Because if life originated twice within this one solar system, that means it was easy. And given similar conditions elsewhere, life will happen. So the number 2 is very important here. So let's now take a look at one of our current attempts to find number 2 in our solar system. In 1995, NASA's Galileo spacecraft arrived at the planet Jupiter after its nearly 8-year-long journey. And a few months after it got there, it began sending us the first high-resolution photos ever obtained of the moon Europa. So Europa is the second closest of the Galilean moons to Jupiter. It's the smallest of the 4. And the photographs revealed a surface that was crisscrossed with cracks and ridges of varying thickness. And that surface is strongly reminiscent of something that we see in the polar regions here on Earth. So on the left, that's a zoomed in Galileo image of Europa's surface, spans about 50 kilometers in width. And on the right, those are cracks in the polar sea ice at Earth's North Pole, and the photo on the right spans a similar width as well. Now on Earth, those cracks and ridges are created by the shifting of plates of ice induced by the liquid ocean that's underneath those plates. And since the Galileo mission also determined using near-infrared spectra of Europa that the surface is composed primarily of water ice, then it's very tempting to extrapolate that the same mechanism is responsible for creating a similar surface structure on Europa. And that could mean that Europa might actually be hosting a global liquid ocean layer under its icy surface. Also, when we compare the surface of Europa to that of other Jovian moons, we find that Europa contains less craters. So for example, on the left, that's the surface of Europa. On the right, that's the surface of Callisto. So that's the furthest of the 4 Galilean moons. And you can see how noticeably different they are in terms of cratering, which is quite interesting because these objects both formed in very similar environments with a common origin. So we know that cratering is indicative of an older surface, right? Because impacts with other objects were far more likely when the solar system was younger and messier. And so one possible explanation for this dramatic difference is that Europa was heavily impacted in the past, but that it contains this underlying global ocean. And if that's the case, then the motion of that ocean could have smoothed out the cratering on the icy surface. And then lastly, a third and very compelling piece of evidence also obtained by the Galileo mission is that Europa's magnetic field is variable. It has a very distinctive cycle to it. And so on the slide here, you can see Europa's magnetic field lines. They're separated into 2 fields, blue lines and green lines. And what makes the 2 fields distinct is that they each have a different cycle, both of which can be attributed to Jupiter's Jupiter's magnetic field, as opposed to a field generated by Europa itself, the way that Earth generates its own magnetic field. And so you can best explain and model the properties of Europa's magnetic field if you attribute its field to a field induced by Jupiter, owing to the presence of an electrically conductive global layer of salt water on Europa. And it was that discovery, combined with Europa's other physical properties, that has allowed us to come up with a theoretical estimate for the depth of Europa's ocean. It is suspected to begin somewhere 5 to 10 kilometers below an icy surface, and then spanning a depth of somewhere between 50 to 100 kilometers. So that is a lot deeper than oceans on Earth. The average ocean depth on Earth is only around 4 kilometers. So Europa's ocean is theoretically at least 25 times deeper than Earth's on average. And even though planet Earth is about 4 times bigger than Europa in diameter, since Europa's ocean is likely global, its dimensions yield a volume of water that's possibly over twice that of Earth's oceans. So how is that even possible? That, 3/4 of a billion kilometers from the sun, we're 5 times further away from the sun than the Earth is. How could an object with a very thin atmosphere and surface temperatures ranging from like minus 150 degrees Celsius to minus 250 degrees Celsius, how on Earth, or more correctly, how on Europa could we expect to find temperatures possible for liquid salt water? And of course, that means we would require temperatures hovering only a few degrees below 0 Celsius. The most likely culprit is the proximity of that behemoth of gravity, planet Jupiter, owing to Europa's size and location within Jupiter's gravity field. Europa is experiencing tidal forces, meaning forces that act more strongly on one side of the object than the other. And since those tidal forces are constantly changing as Europa follows its eccentric orbit around Jupiter, the net effect, it's a sort of kneading of Europa, the way that you would knead dough. And that kneading generates heat from the friction of Europa's physical contents rubbing against each other. And as you can see in the simulation, not only are the top two surface layers affected, so the ice layer and the water layer as well, but also so is the underlying rocky mantle. And that means that the rocky mantle becomes a source of heat. So very similar to geothermal heating on Earth, but a different cause. And therefore, the rocky layer could be capable of heating up any absorbed groundwater enough to shoot it up through fissures in the rock into warm hydrothermal vents. And according to astrobiologists, that could be churning up some of the ingredients for life from the rock into the water, stuff like complex carbon-based molecules, and therefore creating environments very similar to the hydrothermal vents that we have here on Earth. And those regions have given rise to hyperthermal communities of life. So even though these regions on Earth, they're too dark and they're too deep to experience photosynthesis from the sun, and even though oxygen levels are very, very low and the temperatures can get really high, like 60 to 80 degrees Celsius, we find quite a diverse range of hyperthermal extremophiles on Earth, also known now as hypothermophiles. And not just microorganisms, but also some interesting stuff like tube worms and some, furry little crabs, owing to, instead of photosynthesis, the chemical energy generated by geothermal heat, which could instead in the Europa version, that would come from tidal heating. So it's in these near European conditions on Earth where we can expect to find the most similar type of life that we might find on Europa. So on October 14th, 2024, shortly after noon, NASA launched a spacecraft called the Europa Clipper to the Jovian system, and it is expected to arrive in April 2030 after a 5.5-year journey. The Europa Clipper is the largest and most massive planetary spacecraft that NASA has launched to date. It's about the size of a bus, and its main component anyway. And it's got a dry mass of about 3,200 kilograms, so that's somewhere between a Galileo and a Cassini. But once it is loaded up with fuel, its mass nearly doubles to 6,000 kilograms, because once the craft arrives at Jupiter, it's going to need a lot of onboard fuel to complete its mission, and you'll see why that is in just a second. So to get this very heavy thing off of the ground and all the way to Jupiter, it was launched from Kennedy Space Center by SpaceX's Falcon Heavy. This is a launch vehicle that is essentially 3 Falcon 9s strapped together, so there's 2 on each side of a central core. And each of those 3 Falcon 9s contain 9 Merlin engines, which are liquid rocket boosters, and they contain fuel, a mixture of kerosene and liquid oxygen. So that's 27 rocket boosters in total. And altogether, they provide an amount of thrust equivalent to 18,000 airplanes. And that's all used up in the first 4 minutes of launch. In this launch video, it's not entirely real time. It's skipping from stage to stage. You see the 2, you will in a second, you'll see the 2 side boosters. They separate first once they run out of fuel, and then they're followed about a minute later by the central core. Normally, all of those boosters would be recovered by one of SpaceX's autonomous spaceport drone ships so that they can be reused for a future mission, because that is SpaceX's primary mandate, to achieve affordable and sustainable interplanetary space travel by using reusable rockets. And in fact, the side boosters used on the Clipper mission, they are secondhand rockets. They were used to launch NASA's Psyche asteroid mission in October 2023. But to get this heavy craft on a Jupiter-bound trajectory, those first stage boosters, they had to reach a faster velocity than SpaceX is used to dealing with. And so it was decided that an autonomous landing was too risky. The last thing you want to do is spoil a $5 billion launch by missing the catch of its rocket boosters, right? That would not look cool. So instead, the spent boosters were just disposed of in the ocean, and the launch went according to plan. here's the trajectory that the Clipper will follow to get to the Jovian system. And here is approximately where it is right now. So owing to the desire to use as little fuel as possible, because the more fuel the craft has to carry, the more fuel you need to accelerate that fuel, the Clipper will be taking a somewhat indirect path to Jupiter so that it can make use of speed boosts from the gravity of Earth as well as from Mars. So the first of these gravity assists will take place in just a week from now. And what will happen is that the craft will make a flyby of planet Mars. And as it does so, Mars's gravity is going to pull it inward toward the planet, not enough to trap it into orbit, but just enough to speed it up because it's going to be momentarily falling towards Mars. And that velocity boost, or delta V, that's going to place the craft on a larger orbit. That larger orbit is going to bring it back to Earth in December 2026, but now it's going to be moving at a faster speed. And then again, as the craft momentarily falls towards the Earth, it's going to speed up even more, and that's going to place it on an even larger orbit, which will get it all the way to the orbit of Jupiter. So all of that will be accomplished without the craft having to step on the gas pedal once. But once the craft arrives at the Jovian system, that's where things start to get really expensive. At the moment of orbital insertion around Jupiter, Clipper is going to be moving about 1 kilometer per second faster than Jupiter is moving in its orbit around the sun. So that means that Clipper needs to decelerate its 6,000 kilogram self by a delta V of about that much in order to be admitted as part of the Jovian system. So that maneuver will take about 6 to 8 hours of fuel burning, and it will use up about 60% of Clipper's 3,000 kilogram fuel supply. And then after that, Clipper will spend the next 4 years completing up to around 50 orbits of Jupiter, using its remaining fuel to alter the orbit slightly so that it can achieve at least that many flybys of Europa. So those are all the ellipses that you see on the slide. And that's how the spacecraft earned its name, the Europa Clipper. It's a reference to the Clipper ships of the 19th century. Those were those fast ships that were sent on the same trade routes, reflecting the NASA Clipper's frequent flybys of Europa. Based on the current flight plan, the Clipper's closest approach to Europa will bring it to within 25 kilometers of its surface. And it's a neat little exercise to think about how large something will appear in the sky from that vantage point. Just requires some very simple trigonometry. So carrying that out from the Clipper's closest approach to Europa, we end up with, of course, I make my students do this, we end up with the result that if we were passengers on Clipper, then Europa's surface would subtend as much as 86 degrees of sky. So that means that it would cover as much as nearly a quarter of the sky. And that's a pretty cool view to think about, especially given that Jupiter's massive surface would be visible in the background, depending on the angle. And from that vantage point, Clipper's imaging system will be able to achieve a resolution of 0.5 meter per pixel. So 0.5 meter, that is about the length of a really decent sized lobster, which means that if a lobster were crawling around on the surface of Europa, we'd be able to tell. We wouldn't see its yummy claws and legs, but we'd see like a reddish pixel moving around with an obvious lobstery strut, I guess. And then we'd be like, yeah, that's lobster. Now, the Europa Clipper, it's not the only mission currently en route to the Jovian system. It is being chased by an ESA spacecraft called the Jupiter Icy Moons Explorer, or JUICE. And JUICE will arrive at Jupiter about a year after Clipper in July 2031. The mission of JUICE is broader in scale. As its name suggests, it is equipped to explore 3 of the Galilean satellites, Ganymede, Europa, and Callisto. And its view of those objects, they will not be as high a resolution as Clipper's. They'll be at best 5 times lower. That isn't terrible at all, of course. But more importantly, JUICE will attempt to achieve something very historic, which is that in December 2034, if all goes well, JUICE will be inserted into orbit around the largest moon in our solar system, Ganymede. So you can sort of see that simulated here. That would be the first time we have ever achieved orbit around a moon around another planet. And that's an important thing for us to be able to do if we want to, if we ever plan on landing on any of these moons. Also, thank you, John. Also, when both Clipper and JUICE arrive at the Jovian system, they will be greeted by NASA's Juno spacecraft, still in orbit around Jupiter after completing its original mission in 2018. Juno's mission has been extended until September 2025, enabling it to complete about 40 more orbits of Jupiter, including some close flybys of some of the moons. And it is hoped that Juno might be able to assist the other 2 missions in finding a holy grail of sorts. And what I'm referring to is an ice plume. So in 2005, the Cassini spacecraft from its orbit around Saturn took these photos of the moon Enceladus and revealed something really amazing, transient features emerging from the moon's surface, indicative of something being spewed into space. And of course, when we see things being spewed into space, we want to know what they're made of. And so we look at their light spectrum. And when that was done in 2008, what was found is that even at this really frigid region of space, Enceladus is somehow spewing water vapor, which of course is quickly condensing and freezing into ice crystals, just like our breath does on a cold day. So it's like we're seeing Enceladus breathing. If the Europa Clipper is able to find an ice plume on Europa and get at its spectrum, that would be the holy grail of this mission. That would be the moment when the mission has paid for its $5 billion self. Because those ice plumes are coming from the ocean layer. And if we can find out what that ocean layer contains, then that will hopefully bring us closer to determining whether or not this ocean is harboring the ingredients for carbon-based life, which is the sort of life that we somewhat understand. Or at the very least, we might learn what it will take for us to be able to land on Europa's surface and send down some really brave robotic scuba divers. As it happens, in 2014, the Hubble Space Telescope imaging spectrograph picked up a flare of ultraviolet at wavelengths associated with water vapor on Europa, and it was seen again in 2016 at the same location, suggesting that this might be a location of ice plume activity, and that perhaps there's other locations as well. So the hope is that when Clipper and JUICE arrive at the Jovian system, that Juno will be able to very graciously direct them to the best viewing locations for these ice plumes. In 2005, the film director James Cameron, known for really far out movies like Alien and Avatar and The Abyss, he created a documentary called Aliens of the Deep. And this film explored a part of the ocean in which we find really unusual aquatic life, so unusual that it seems alien. And at the end of the movie, the documentary shows us with CG what a potential ocean exploration mission to Europa might look like. So that's what you're seeing in the video, a mission in which we actually drill through the surface ice until we reach the liquid ocean, and then we send a submersible probe to explore the ocean for life. And when I first saw this documentary several years ago, I never forgot the very last scene of the visualization, which you're going to see in just a second. I think. Yes. Right. So, I've tried to imagine what the response would be at mission control. They're all watching their screens. and they're watching images being sent back to Earth, and then suddenly some sort of European mermaid appears on the screen, right? Like it's just, you can't imagine what the response would be. Now you're probably thinking, and rightly so, that this is just James Cameron's overactive imagination blurring the boundaries between his crazy sci-fi movies and reality. And we shouldn't get caught up in this kind of sensationalism. But the truth is that even if this is all we find, you know, a community of creepy crawlies, possibly not even visible to the naked eye, maybe we will only find weird little microscopic silverfish or maybe just bacteria. Even that, the reaction here on Earth would still be like a freak out, the size of which the solar system has never seen. Because it would finally mean that we have found our number two. And if there's a number two, there's far more likely to be a number many more. And therefore, we can finally assure ourselves that we are not alone, we're not a fluke, despite the loneliness and solipsism we may feel sometimes when we contemplate the silent treatment that we get from space. We are not freaks of nature. That's it. I hope I said at least one new thing that you didn't already know. And thank you all for being such an awesome audience.
My question is, are there estimates of the temperature of the liquid ocean underneath the ice cap?
That's a really good question. Not that I know of. So right underneath the ice cap.
Well, it's pretty well insulated. So
yeah, I don't know. I don't know. Let's look it up during the break. But that's a very good
I guarantee you right there, it's 32 degrees Fahrenheit.
That makes,
Yeah,
I understand.
yeah.
Or because you said that salt would actually lower.
A little bit lower, a little bit.
And it's under pressure.
Yeah, I think the idea is that there's potentially a lot going on.
Yeah.
There's also, you know, how do you get oxygen down there, right? So there's these theories that there's like vertical melting chambers, like constant, almost like a waterfall inside of this thing. Constant melting that's going on, dripping down. Like how else would you get oxygen down to the surface, right? If there is oxygen down there in communities like we have here on Earth. So there's a lot of processes going on right at the surface, and hard to say what the temperature constraints would be.
Okay, up there. Joe, is there indication of an atmosphere?
Yes, very, very thin.
There's some notion that on Earth might come in comets.
Right.
We have this pinkish moon that seems to have a lot of water.
Not the only one, but yeah. No, that is a really, really good question. You know, Enceladus is also displays similar features, but you know, Callisto, not so much. It's some signs maybe, but not nearly as much as Europa. So why? You know, why in the same environment, why some moons have water possibly and others don't? A really, really good question.
Should go there and find out.
We totally should.
Hi, everybody. So I'm part of the awards committee. That's why I'm up here. So I have a very, it's my honor and my privilege to award the Special Project Award. And it is with great pleasure that we recognize Val Connery. So I'm going to read out the nomination. For her outstanding contributions to our center, Val's tireless dedication and organizational skills have been instrumental in making our picnic a resounding success year after year. From securing the perfect picnic site to coordinating food orders and arranging the ever-popular ice cream truck. I love the ice cream truck. Val ensures that every detail is thoughtfully planned and executed. Her efforts in setting up the picnic site create a welcoming environment where members can connect, relax, and celebrate their shared passion for astronomy. We're deeply grateful for all that Val does and are honored to recognize her with this special award. Congratulations.
Swapna, a dedicated member of the Mississauga Center, deserves a recognition for her contributions to the center. Swapna was the center secretary for a number of years and is currently on the awards program, the new members welcome committees. Swapna organizes the potpourri and speaker nights and sometimes hosts the meetings. She also sometimes participates herself in the potpourri nights, sharing her knowledge and enthusiasm with her community through informative presentations. In addition, she organizes and oversees special events for members, such as visiting the meteorite collection at the Royal Ontario Museum and visiting the York Observatory. For our annual picnic, Swapna started the Astro Exchange and runs it every year. When she can, Swapna also comes out to Riverwood with her telescope to participate in the center's public outreach program. Swapna's contributions to the center have made her a valuable asset to our club. Her dedication, organizational skills, and commitment to the center have earned her the Center Award. Thank you, Swapna.